Hi everyone out there on the internet. I hope you are having nice and hybrid times. First of all, I would like to thank the entire NIME 2020 team for this exhaustingly well-programmed conference covering as many time zones as possible. I can imagine the work behind it and appreciate it immensely. Okay, my name is Çağrı Erdem, and today I will tell you about a system we developed called Cavi, which is an audiovisual instrument that uses deep learning to generate control signals based on the performer's body movement. After mentioning my motivation briefly, I will explain the data and the building blocks of the system and how I think it ended up being a sort of an instrument composition hybrid. But first, let's see a little excerpt. So what happens here is that you play your instrument with some effects, but someone else is tweaking the knobs. So you basically control the same sound and music parameters, which I call as shared control. Such kind of control can be similar to some multi-user and feedback NIMEs. What's particularly counterintuitive in Cavi, though, this person or thing that tweaks the effects knob is not a professional musician or anything, but you can imagine it as just a toddler that can only look at you and imitate your body movements with limited cognitive and motor abilities. But why the hell on earth do I want that? Isn't it so annoying that a goddamn toddler messing up with your years-long instrumental practice and delicate artistic ego? I have two motivations for that. First is an exploration of new artistic repertoires, new performative intentions, or perhaps even non-intentions, as in John Cage's famous Exploration. Second is developing artificial musical agents that interact with the human performer mainly based on their body movement. In order to do that, I have used some embodied music cognition concepts and theories. We use our bodies to interact with music in many different ways, and so there are quite several types and categories of music-related body motion. Among them, we focus on sound-producing actions, which are responsible for note production on musical instruments. Then the sound-producing actions can be further divided into excitation actions, such as the right hand that excites strings, and the modification actions, such as the left hand modifying the pitch. The excitation can then be further divided into three main categories according to the gestural sonorous objects model that is created by Pierre Schaeffer and presented by Rolf Inge-Guroy. These are impulsive, sustained, and iterative. Using this concept of fundamental motion types, we collected a multimodal dataset throughout a series of experiments with 33 electric guitar players as part of a previous project on a deep learning-based action sound mapping, which you can check with the QR code here. The dataset contained muscle sensors worn on both forearms, motion capture, video, and sound recordings of the guitarists playing tasks and free improvisations. We shared the dataset with an open access, so you can just download and start exploring yourself. In that project, the predictive accuracy of our mapping models showed that it could learn the constraints of human body based on a dataset of only fundamental motion types. Then in Cavi, we wanted to explore that further, and so what the model can generate within those boundaries in terms of novel control signals. To explore that, this time we focus on muscle and acceleration signals only from the my armband placed on the right forearm in order to create artificial excitation actions. That's because our previous study showed that excitation action provides the main dynamic characteristics of the sound, and it's much more generalizable compared to modification actions. So we implemented a model that continuously tracks the performance multimodal motion input consisting of 4-channel electromyogram corresponding to extensor and flexor muscles and 3-channel acceleration data. The Python script for the live performance first extracts the root mean square feature of the EMG and moving average of acceleration. which are then buffered in windows and queued in simultaneous thread to be fed into the model. The model uses 2 long short-term memory layers with 64 hidden units, combined with a mixture density network, which transforms the output of the network into mean, weight, and the standard deviation of a Gaussian mixture model. These parameters are then sampled to generate real-valued predictions. In the generation phase, Performer can dynamically adjust the model's level of randomness by tweaking its parameters such as weight and distribution temperatures. For example, a larger weight results in sampling from different distributions at every time step. So the Gaussian distributions in the scenario can be thought analogically as the possible action sequences, in our case in the form of EMG plus acceleration. So in other words, when our model generates a sequence, it's just one possibility among many where there is not an ideal answer. Our aim with this approach was that the model could learn the boundaries of sound-producing actions on musical instruments such as guitar or drum set. And so within these boundaries then, we wanted to explore what can surprisingly emerge between the performer and the system. So in Cavi, the musical strategy is based on live sound processing in the context of collaborative improvisation. The system continuously generates new EMG and acceleration data akin to the musician's excitation actions. The generated data then are used as control signals mapped to parameters of digital audio effects modules. These effects modules that Cavi control primarily rely on time-based sound manipulation such as delay, time stretch, stutter, etc., all designed on MaxMSP. The measured jerk of the generated or the artificial acceleration somewhat embodies an excitation action and triggers the sequencer which routes the signal in and out the FX modules, while the parameters of these modules are controlled by other features extracted from the generated signals. The performer can also use the sequencer grid as a compositional tool by drawing patterns and then editing or calling these during the performance. Moreover, Cavi listens the audio events and regulates itself as well. For example, if the performer plays impulsive notes, Cavi increases the reverb time drastically, such that it becomes a drone-like continuous sound, and so on and so forth. Finally, Cavi is an audiovisual instrument for aesthetic reasons and to relieve potential causality ambiguities. Its virtual body is first hand-drawn by Katya Henriks and Chia, which I digitized afterwards using a particle-based design on Max Jitter. We envisioned Cavi as an uncompleted, creepy, but cute creature. In its premiere performance, 2 professional musicians performed with Cavi, the guitarist Christian Winter, who you can see also in the picture, and the drummer Dag Erik Knedel Andersen, who was in the video excerpt earlier, both from Norway's jazz and improvisation scene. On stage, Cavi was embodied through a human-sized screen and a hemispherical speaker playing around the same level as the acoustic guitar. In summary, different modalities such as EMG and acceleration signals overfit and generalize at different rates, so training them jointly with a single optimization strategy is not optimal. The predictability of generated elements, and so how much the agent is perceived as surprising or dull, varies over time through a dynamic interplay between randomness and order. Time-based multi-layered effects can occupy most of the frequency spectrum, and for that reason, it can sound less overwhelming with non-pitched percussive instruments. For example, in terms of traditional ideas of artistic ownership, we still don't know how to properly register the first performances in the Norwegian system. Who should be registered as the composer of the pieces performed? Who performed? Who made the sound? The performance space, microphone setup, and monitoring system are parts of the dynamic processes of musicking, and thus all contribute to the agency assigned to the musical agent. Of course, the human embodiment cannot be reduced to a single 4-hour measured as 7-channel data. Thus, Cavi is still developing and learning, and it can be best described as a musical AI toddler. Cavi has instrumental qualities, but it more resembles an advanced effects module. However, the development process also included compositional thinking, so in many ways, it can be seen as an instrument composition made by a programmer-composer. And as for concluding remark, we want to emphasize that the technologies we use to make music carry agency, and how we use these technologies strongly influence the music we make and our future at large. Hope to see you all in the 4th music session on Friday, where I will perform with Cavi together with 6 self-playing guitars as the closing act of the session. Thank you.